Welcome to COMP3311 Database Systems. This course, as the name might suggest, is heavily related to data. So the whole course deals with various aspects of data, manipulating, storing, sharing, and so on and so on. All right, well, database systems are systems that store, manipulate, allow you to share, and allow you to check the integrity of your data. So often we'll draw a database system looking like a giant disk drive, something like that. It's not a great disk drive, but it will do. And on this database, we store a whole lot of data. I'll talk about the structure of that data in a moment. To manage that data, we need a database management system. And so a lot of the focus of the course, as well as being on the data, is on the systems that manipulate that data. So what do these DBMSs actually do? Obviously, they manage the storage of the data. So they allow you to store very large amounts of data. We're talking not 10,000 records, but 100,000 or 1 million or 10 million or a billion. And nowadays, things like Google store extremely large amounts of data. So some mechanism for storing data, a mechanism for asking questions on the data. So we need some way of, obviously once we've got a whole lot of data stored on the disk, we can't just look at it in total. So we need to have ways of extracting the data that's interesting to us. One very important thing that that database management systems do, and the ones we're looking at, as I just hinted, are relational database management systems, is they allow us to check the integrity of our data. So when you're trying to add new data to the system, the DBMS will check that it fits a certain set of constraints that you define as part of your database structure, and only if the data makes sense will it be inserted into the database. And one other very important thing that DBMSs do, as soon as you've got a large amount of data, lots of people are interested in it, and therefore we need to be able to share data. Now, the first couple of things, potentially, or certainly the first one, you can do with a straight file system. No problem, we know, I'm sure in one of your other courses you would have written structs or records to a file, and then you can retrieve those records from the file at a later date. So that aspect of databases could be handled with a file, just with a file system. These can't, and in particular sharing, the notion of enforcing concurrent access to the database in a sensible way is something that's a lot harder to do with a file system. Similarly, generic styles of checking the validity of data is also hard to do. All right, so what kind of data are we talking about? We're talking about relational data. Relational data has an extremely simple structure, and basically it's just a vast collection of tuples, where a tuple is just a collection of values. So how many values in a tuple? Well, as many as you like for the application that you're implementing. If we've got a set of tuples where each tuple has the same number of items and the items are of the same type in each tuple, we can take that set and we could call that a relation. And in the DBMS world, that's also implemented as a table. If you think of a spreadsheet, it's a similar kind of idea. So everything is implemented as a collection of tuples. And you might say, that's a pretty simple data model. How can you implement everything as a collection of tuples? Well, it turns out that you can't implement everything, but you can implement such a large set of useful applications that this has become the dominant data model in computing. Another very important thing about the relational model is that it's extremely simple sets of tuples, and it maps really easily onto typical storage structures that we have in current computer systems. So I'd argue it's one of the nicest parts of computer science that we've got a model, a theoretical model in fact, and it has lots of interesting theoretical properties that we'll also look at through the course, but it maps very easily onto computer systems. So there's not much of a distance between this very nice theory and this implementation in practice, which is an extremely useful implementation. All right, so that's data. Obviously, to deal with data, you need to have some kind of database systems. The first thing is that relational databases are all based on, pretty much all based on the language SQL. SQL, structured query language, was initially developed just as a query language, but it also has a sub-language for defining data. So you can say, I've got a table which has a set of tuples. Each tuple has 3 components. The first one is a student identifier, say, second one is a student name, and the third one is the program that they're enrolled in. So SQL, very important. It's pretty much a standard formalism for manipulating data and has a number of implementations. We'll be looking at 2 of them. The first one is the Postgres database management system. So the QL is silent, we just call it Postgres, and Postgres is a pretty standard client-server system. So we've got a server that manages the data on disk, clients, which can be web applications, could be C programs, could be Python programs, could be PHP programs, send requests to the server gives them back collections of tuples, which they can then render to the user however they like. So Postgres client-server system. A slightly simpler DBMS is the SQLite system. It doesn't work as a client-server system. It works by having a program that manipulates a single file, but still provides all of the benefits of the SQL language. All right, so what topics are we going to cover in this course? Well, obviously we're going to talk about the relational model, and we're going to talk about how you start from a description of a problem and how you develop a data model to represent the data in that problem in such a way that you can then manipulate it using all of these things. So data modeling is the first thing that we'll talk about. Having talked about data modeling, we will then get onto SQL, and so talk about query language. The SQL query language is actually quite powerful, and we would call it a logical language where you're not so much specifying, go and fetch this tuple from this location on the disk. You're simply saying, I want a bunch of tuples that satisfies these properties, and the DBMS goes and gets them for you somehow in a way that you don't need to worry about. While SQL is a very nice language and useful, powerful for asking queries and so on, it's certainly not a complete solution to writing database applications. So at some point we need to involve a more conventional programming language which can then use the power of SQL to extract data from the database. So there's going to be a discussion of the interface between programming languages and databases. And PostgreSQL has a number of interfaces to a whole bunch of different languages and at various levels of abstraction. So one level, very low level, there's a C programming interface to PostgreSQL. At higher levels, you've got things like an object relational mapper for Python. So putting these things together, we can build database applications. Before we could build the database applications, we needed to come up with a data model. And another important aspect is trying to work out how good our data models are. And there's a whole theory that allows us to deal with that, the theory of functional dependencies. And since those words are very long, I'm not going to write them in full. They talk about how the relationship between individual attributes in a tuple, essentially. So we'll look at functional dependencies as a basis for talking about how good a data model we developed initially. One other important aspect of databases is that they talk about sharing, and the whole notion of sharing is tied up with the notion of transactions. So when a person logs into a banking system, say, and wants to transfer money between accounts, there's actually multiple database operations that take place, but the individual database operations have to all work together to produce a final operation that makes sense in the context of the application. So we deduct money from one account, or first thing, we could check that there's enough money in the source account to deduct, then we deduct it, and then we add it to the destination account. So potentially there's 3 database operations involved there, but together they work as a single operation transfer. And transactions talk about how we can reason about making sure that either all of those operations succeed and we get a transfer taking place, or nothing succeeds. So anyway, that's the notion of atomicity of transactions, and we'll talk about that as well. And finally, while I've said the relational model is beautiful and SQL is a nice implementation, there are some things that don't work particularly well under the relational model, and there's a whole lot of applications which you might just in general call non-relational applications that have had their own specialised database structures developed for them. So we'll have a brief look at them at the end of semester. So the relational model gets you 99% of the way to your average application. In fact, it will probably get you 100% of the way to your average application, and it will do that for 95% of applications, but there's a few applications that require other kinds of databases that, rather than modelling tuples and relations, they model things like graphs. Okay, so that's a complete picture of what happens in COMP3311. I hope you enjoy studying all of these topics throughout the rest of the semester.